So there's one last type of error that we need to contemplate, and it does not show up in the uncertainty because it's a type of error that should really be eliminated. And this type of error is called systematic error, and that essentially means that you're making some error in the measurements in a consistent direction, meaning that, for example, there's nothing wrong with this ruler, except that for some people they might not notice that the 0 is not at the very end of the ruler. There's actually about 2 or 3 millimeters from the end point. Now if I didn't notice that and I just assumed that, and it is true on many rulers, that the edge of the ruler is actually the edge of the 0, the starting point, then when I make all my measurements will be a little bit big by about 3 millimeters or so. Or by contrast, when we look at meter sticks, oftentimes some of the older meter sticks have sort of worn away the ends, and of course the end is actually where the 0 is supposed to be, and so they may actually be slightly shorter. They also suffer from problems where they may expand or contract in the various temperature changes. So essentially the systematic error is oftentimes the measuring device, or it could be a combination of the way that the observer is using it. A good example is if you notice that the meter stick has a little bit of thickness, so when you make a measurement, for example, so from where I'm standing right now, I can't see the edge of the C right here, even though I know that if I move my eyes directly over it, I will be able to see it. So when I make a measurement with a meter stick, since this is not completely flat to the ground, I need to make sure that I put my eye directly over the edge of this thing. Now if I don't, I consistently make my measurements from this direction, then that's going to misrepresent the length and make everything seem longer than it is, because I haven't actually lined it up with the edge of where I'm trying to measure to. So most often in the measuring device, but occasionally the observer may play a role that causes a systematic error, or may even be the only reason for the systematic error. One of the issues with the systematic errors is that you would obviously like to not so much reduce it, but try to eliminate it as much as possible. And the problem with it is that you would not be able to reduce it by simply making a lot of measurements. That reduces the random error, but it doesn't have anything to do with the systematic error. If you made the mistake of measuring from the 0 here, if you were to use this same ruler 10, 15, 100 times, you would probably still do the same thing and not notice that you were just not measuring from the 0. If you make the mistake once, you're probably going to make it more than once. And essentially what that does is create something that's a little bit different than what we would expect. More often than not, you would expect that when you compare one variable to another, if there's a relationship between the two, when this variable goes to 0, this variable probably would also go to 0. So in most cases, the majority of cases, we would expect that whatever relationship we get, whether it's a straight line or whether it curves up or curves down or whatever its shape, it goes to the origin. As the variable on the x-axis goes to 0, the variable on the y-axis also goes to 0. But in the case of the ruler, I would be making everything seem like it was, in this case, it would actually be shorter because I'm not counting this distance, this 3 millimeters. So the numbers that I'm reading off down here are actually a little bit short. So in that case, that would cause this to shift downward. So the relationship is right. You see, the relationship is right. I can see the shape of the graph, but the graph has been slid around so that it doesn't represent what's the accurate phenomena. If by contrast I used the meter stick that had the end worn off, then in that case I would be making all of my measurements longer and I would see the line rise up. That is to say, at the same point along the x-axis, I would find that the value was higher than it really was because of this systematic error. These type of errors we really would like to get rid of, or at least acknowledge that it seemed likely that there was systematic error, and why did that happen? When you see that you don't hit the origin, you should think back to the measuring devices. It probably had something to do with the measuring device, but it could be something that you did. And you don't have to go back and change your data. You just simply need to explain where you think this source of systematic error may have been located. Besides the systematic errors that result from just measuring devices like this, we also need to think about both calibrating the devices and checking for the 0 error. They're basically ways of making sure that the measuring instrument is still measuring accurately before we go and make the measurements of the real phenomena. Calibration and 0 error actually are two different things. Calibration has to do with making a comparison of an object which has a known value to a very high level of precision to what the device says. So for example, I might make some measurements and measure something that I know for a fact is exactly 5 centimeters long. And then I may compare it to this ruler and find that the object appears to be a little longer or a little bit shorter. And if I know that the object that I'm measuring is exactly 5 centimeters, then obviously there must be something wrong with the ruler. In the case of rulers like this, they may expand or contract in the hot or the cold weather, and so that may cause the whole thing to stretch or contract. So everything will read large. No matter where I measure on the ruler, everything will be measuring a little bit large. That's what's called a calibration error. Another calibration error would be a stopwatch that runs too fast. So every measurement will be off. The longer you make the measurement for, of course, the more it's going to be off. Because of the fact that it's running faster, every second that it runs faster, there builds up a little bit of a difference between the real time and the time that you're measuring on the stopwatch. So that's called a calibration error. A scale is an example of something that you might calibrate. If you have a bathroom scale at home, there's probably a little dial on the side that allows you to set it to 0 before you get on it to make sure that it's going to give you an accurate reading. Second thing is called the zero error. So the zero error is essentially that when you have nothing on the device, it measures 0. So most devices don't suffer terribly from this problem. A lot of electronic devices that you use might suffer from the zero error if they're measuring things like, for example, the voltage or the current. Oftentimes those things may have a zero error that you need to check, and that is that when there is nothing connected to it, they're not reading any value. Because obviously that means that the whole thing has been set off, and this is where something that you would fix on the bathroom scale by flipping the little dial to set that back to 0. So these are two types of errors that you need to things you need to think about when you're trying to establish whether there might be systematic error. And of course, if you expect it to go to the origin and it goes to the origin, then that probably is a good indication that there's not a lot of systematic error. If you see that there is, you would look at how far is it. Is it very close? Maybe that's just within experimental error. Is it really far, way beyond what the experimental error, the uncertainty, would say about it? And so in that case, you really need to go back and think about the measuring devices that you use to make those measurements.